Hi everyone, this time we are going to have a look at the pigeonhole principle. This is one of the newer topics in this course, and the principle itself is pretty straightforward. It deals with counting. So let's say we have 11 pigeons and 10 holes. Well, there's guaranteed that at least one hole will have at least two pigeons, isn't it? So basically, at least two pigeons in at least one hole. Yeah. Of course, it's just the minimum condition. Maybe you have all 11 pigeons into one hole, or five in one and six in the other. But either way, this condition is satisfied. However, if you have less than 10 pigeons, then this condition may not be satisfied, because if you let's say you only have 10 pigeons. Sorry, if you only have 10 pigeons, then there's a possibility that you only have one pigeon per hole, and you cannot satisfy this condition of two pigeons in one hole. So even though it may still be possible to have, say, 10 pigeons and five per hole for two holes, but it's not a guarantee. Yeah. So one key thing with pigeonhole principle is we're always looking for guarantees. We are looking for the worst case scenarios. So for example, well, it's more obvious in this kind of situation. So if we have 10 holes, how many pigeons are required to guarantee at least one hole will contain at least 8 pigeons? Of course, it's possible to satisfy the condition of at least one hole containing at least pigeons by just having 8 pigeons in one hole. Yep. That's possible. That's a satisfied condition, but it's far from guaranteeing it. Yeah. So the key word here is to guarantee. Now, what's the worst case scenario? The worst case scenario is the pigeons come in and they fill up the 10 holes, but end up with only 7 per hole. So 10 times 7 equals to 70 pigeons. Yeah. So this, of course, it's possible that 70 pigeons can satisfy this condition. But in the worst case scenario, if all 70 pigeons gets distributed evenly, this condition will not be met. And only way to meet this condition is to add extra pigeon. Yeah. So that even in the worst case scenario, when all the holes are filled, you still have this extra. So even when all the holes only have 7 each, you still have this extra to bring at least one hole to at least 8 pigeons. Yeah. So it doesn't really matter how these 71 pigeons are distributed really. You can have all 71 into one hole, let's say 36 in one hole and 35 in another. It doesn't really matter, but we are dealing with here with a pigeonhole principle is we're always looking for the guarantee, the worst case scenario. Yeah. Let's run through some examples. So for example, 70 guests sit as a restaurant with 23 tables prove that there must be at least one table, at least 4 guests. Well, so think about what's the worst case scenario. So all 70 people are distributed evenly amongst 23 tables, yeah? So what we end up with is, so 3, remainder 1. Yeah? Okay, so we know that 23 tables, 70 people can fill 3 in each table. Yeah, so that's guaranteed. And then one extra person will bring at least 1 table, will just bring 1 table to at least 4. Of course, once again, all 70 people could be sitting on the same table, or maybe 7 each on 10 tables. But it doesn't matter. We are looking for the guarantee. We're looking for the worst case scenario. Yep. So that's it. So 70 people guarantees that these at least 23 tables will have 3 people each, and then we'll have this extra one to bring one of the tables to 4. Now, if we go the other way around, I explain how many guests there must be to guarantee at least of the one of the 23 tables have at least 11 guests. So of course, once again, minimum, we can have 11 guests and they all sit on the same table. But that's far, far from guarantee. Yes, so the keyword is guarantee. The worst case scenario here is we have 10 people, 10 each, on these 23 tables. Yep. And we have 230. So 230 cannot guarantee that at least one table will have at least 11. We need extra person. 230 can only guarantee that each table will have 10. Yeah. To make sure that we have 11, we need to introduce this extra person. So 231. Yeah, only 231 will guarantee that. Yeah. So once again, we're looking for a worst case scenario and something that will guarantee that we get over it. Okay, let's move on. So here's one very similar. Now, if shopkeeper knows 200 people from these 15 apartment blocks, explain why he must know at least 14 people from at least one block. So, of course, 200 people, maybe all 200 come from the same block that satisfy this condition. At least 14 people from at least one block. Or if 20 each from 10 blocks still satisfy this condition. To show that this guarantees it. This 200 people from the blocks guarantees that know at least 14 people from at least one block. We can once again go back to the worst case scenario. Like, what if these all 200 people are evenly distributed among these 15 blocks? So equals to 13, remainder 5. Yep. So in this case, even if all these 200 people are evenly distributed amongst 15 blocks, that guarantees 13 people in each block plus 5 more. So that means he will know at least 13 people from each one of the 15 blocks, and then there's extra 5 people that can bring the numbers in some of these blocks to 14 or above. Yeah? So that's how you do it. Now, if we do the other way around, how many people from these blocks must he know in order to know at least 25 people from at least one block? So once again, it's entirely possible that all these 25 people come from the same block. But that's not a guarantee. To guarantee that he will know at least 25 people from at least one block, then he has to know 24 people from each block. Yeah. So this guarantees that if he knows, 360. So if he knows 360 people, then that guarantees he knows at least 24 people from each block. And then one extra person he knows will bring at least one apartment block to over 25. Yeah. So worst case, so of course, if we have number less than 360, it's entirely possible that some of them, like, there's a chance that 25 of them will come from the same block. But that's not a guarantee, because the worst case scenario is if you know 360 people, 24 each comes out of the 15 blocks. So you don't meet this condition. You have to add an extra one person to guarantee that this condition of at least 25 people from at least one block is met. All right, let's try another one. So this one's slightly different, but we can approach exactly the same way. So obviously, in this case, the number of hair is are the holes. Yeah, so it goes from 0 to some number less than 5 million. So you either have a 0 strands of hair, so it should be strands. So 0 strands of hair on your head, or somewhere just a little bit fewer than 500,000 strands. Yeah. So okay, so just like to less than 5 million. Yeah. Okay. So 500,000. Now the population of Sydney. So these are the pigeonholes. Yeah. And the number of population. So the number of pigeons is more than 5 million. So if we have exactly 5 million people, and so exactly 5 million pigeons and exactly 500,000 holes, then we'll have 10 pigeons per hole guaranteed. Yeah. But here, fortunately, what we have is less than 500,000 strands of hair and more than 5 million population. So let's just bring one up and change one. Yeah. So more than population of more than 5 million. And then the number of strands of hair is less than 500,000. Then we have 10, remainder 11. Yeah. So once again, it guarantees it that at least 10 people will have the same number of strands of hair, and then there will be 11 more hanger-ons that will bring the number to 11 at least. Yep. Of course, it may not distribute this way. So once again, if you may still have, say, all 5 million people have the same number of strands of hair on their heads, but that is not a guarantee unless the number of pigeons is more than 5 million and the number of holes is less than 500,000. Yep. Okay, next one. So this is an interesting one because the crux of a question like this is to identify what are the holes and what are the pigeons. So this guy has 30 ties, and every day he picks a tie at random. Yeah. So how many successive dates are needed to guarantee that there's at least one day of the week on which he has worn the same tie on at least 6 occasions? So because he mixes his ties and the days, so we're trying to find, say, how many times he would have worn the same tie on a Wednesday 6 times, or on Thursday 6 times, and so on and on. Yeah. Now, in this case, the pigeonholes are the specific day of the week and the tie combos. Yeah. So you end up with 30 ties times 7 days of the week, 210 possible tie day combos. Yeah. Okay, so now we're looking at how he will cycle through these combos. So that means to make sure we want to find a specific tie-dye combo has happened on 6 occasions. Yes? So that means every specific to guarantee that at least one tie-day combo has occurred 6 times, we have to make sure that every single other tie-day combo has occurred 5 times. Yeah. So it means that every possible combination of tie and the day of the week has occurred 5 times. So that's what's this? 1,050. Yeah. So only after 1050 days, there is a guarantee that there's every a tie and the day of the week combination has occurred 5 times. Of course, there maybe he does it. Maybe he flunks, like, or rather he flukes it, and takes only 6 weeks and 42 days to achieve the same tie and weekday combo on 6 occasions. But that's not guaranteed. The only way to guarantee that he will have the same weekday and the tie combination is to make sure that every combination has occurred 5 times at least. Yeah, and then this one extra occasion of a particular tie and date combo will add to one of the rest. So it means 1050 plus 1 equals to 1051. So that's the guarantee. Yeah. So even though anything less, it may still have specific combos, like specific tie and the weekday combination may still occur more than 6 times, but that's not guaranteed, because the worst case scenario is everything gets distributed evenly. So over 1050 days, every tie date combination occurred 5 times. Yeah. So only way to guarantee it one extra time. So I guess the trick here is to recognize that the tie and the date combo is the pigeonhole, and the number of days are the pigeons. So just be aware. Let's move on. So next one is interesting because the way to find how many holes are there is slightly tricky. So 15 people come into a room. There are many handshakes as they meet. So no pair shakes hands twice, and no one shakes their own hands. Yeah. So that means there's a potential for each person to shake between 0 to 14 hands, isn't it? But when you really think about it, these two are actually mutually exclusive. If one person has shaken 0 hands, then no one else will be able to shake all 14 others. Yeah. So the maximum possible handshakes, if someone inside the room has shaken no hands, is 13, because the maximum number of possible handshake is with the 13 people apart from the person who has not shaken any hands. So that's the first scenario. And if someone has shaken hands with everyone else, then there can be no person in the room who has shaken no hands. So at minimum, one person will have shaken hands with the person who shook everyone else's hand. Yeah. So the next one is 1 to 14. So these two scenarios are mutually exclusive. You either have someone who have shaken no hands, and the maximum number of handshakes in the room is 13, or if one person has shaken all the hands, and the minimum number of handshakes in that room will be 1. But either way, the number of handshake will be the pigeonholes. So 14 holes and 14 holes here. Yeah. So it doesn't really matter which scenario was the case. So 14 holes, that guarantees that if we have 15 people divided by 14, we have 1 remainder 1. Yeah. So we can guarantee that at least one person will have shaken any number between 0 to 13 or 1 to 14 hands, and then plus one extra person can bring one of those number of handshakes to 2. Yeah? So that guarantees two people will have shaken the same number of hands. Okay, so next one. Here's a interesting one. So how many odd numbers less than 20 must be chosen to guarantee that two of the chosen number add to 20? Well, so firstly, we have to figure out how many numbers, odd numbers, less than 20 add up to 20. So let's say the first one is 1 and 19, isn't it? And the next one is 3 and 17. Next one is 5, 15. You know how this goes. 7, 13. 9, 11. And of course, oh, that's it. Sorry. So, what was I thinking? Oh, yeah, sorry. We'll cycle back 11, 9, but it's the same. So, how many odd numbers must be chosen? So once again, think about the worst case scenario and think about what guarantees. So of course, the worst case scenario is you start picking, you pick 1, you pick 3, you pick 5, you pick 7, you pick 9. Yeah. So all of them, none of them will form a pair. They will not form a pair. So you need a sixth one. Yeah. So only when you pick sixth one, it will guarantee that one of these 5 pairs will form. So if you only pick 5, then there's a chance you'll only pick 1 from each pair, and you will not have a pair that adding up to 20. So only if you have picked 1 more, then you can guarantee that one of these pairs will have formed, and you will have a sum of larger than 20. So you need to pick 6 numbers. Yeah? So that is how you deal with something like this. Okay. Now is a pretty tricky one. Yeah. Use the Pigeonhole Principle to prove that there are 2 powers of 2 that differ by a multiple of 8,479. So we are basically looking for 2 to the power of A minus 2 to the power of B. Yeah, 2 powers of 2 that differ by a multiple of where n is a positive integer, I guess, because I don't say it's a natural number, but a natural number could be 0. Yeah, it'll define. So basically, that's what we're looking for. However, we're just proving that these 2 powers exist. Yeah. There are 2 powers. We don't actually need to find out what A and B are specifically. So that's one of the tricky part. So how do we know that there are 2 powers that can accomplish this? The 2 powers will have a difference of a multiple of 8,479. Well, that will require us to look at property of remainders. Actually, probably the best way to look at it is through modular arithmetic. It's not that terrifying. So the idea of modular arithmetic is where you have a number system that cycles back to itself. Yeah. So for example, basically like your clock. So it goes from 0 to 11, and then it cycles back to 11. Sorry, cycle back to 0. Yeah. The thing is that the same property applies for remainders. So in this case, say 0. Let's say the modulus 3 is basically we're looking for the remainder of 0 when divided by 3. Yeah. So the modulus 3, which equals to 0, because 0 divided by 3 is, gives no remainders. So 1 mod 3, that gives 1, because 3 goes into 1 0 times with the remainder 1. So 2 mod 3 gives us 2, and 3 mod 3 because 3 divided by 3 has no remainder, so we get 0. And that's what I'm talking about, like when I'm talking about cycling, yeah? So 4 mod 4 equals to 1 again. 4 mod 3, my bad. So 4 mod 3, so 4 divided by 3 is 1 with remainder 1. So all of these are remainders. Mod 3 equals to 2, and 6 mod 3 equals to 0 again. So the cycle continues. As you can see, a cycle every 3, yeah? Now, what's the main feature of these numbers that have the same remainder? So let's look at 2, yeah? So 2 mod 3, yeah, this one, or if we continue on, what's the next one that will have mod? So 8 mod 3 equals to 2, yeah? And go on, and what's that? 11 mod 3 also equal to 2, yeah? So these numbers will have the same remainder when divided by 3, okay? Wait, what happened there? Okay, so these numbers, they will always give you the same remainder when divided by 3. So in the language of a modular arithmetic, it means they are congruent. So basically, we can say that 2 is congruent to 11 when modular 3. Yeah, so that's just a different way of saying, and they give you the same. They give you the same they give you the same remainder when divided by the same divisor. Yeah. Okay, so one interesting feature is that the difference between congruent numbers for a specific modulus, 11 minus 2 equals to 9, isn't it? Which is a multiple of 3. Yeah? Or alternatively, 8 and 8 and 4, isn't it? 8 and 5. So or 8 is congruent to 5 with mod 3. Yeah. So that means 8 minus 5 equals to 3, which is also a multiple of 3. Okay. So because as you can see here, the remainder ticks over each time you complete a cycle that's equal to the number of divisors. So it's a cycle of 3 because you divide by 3. Yeah? That means all the number that produces the same remainders, because the size of the cycle, they will always the difference will always be a multiple of the modulus. So in this case, 3. So there, now it works for everything else as well. So for example, let's say 6 mod 5 is equals to 1. Yeah. What else divided by 5 give you a remainder of 1? Let's say 31. Yeah. So it cycles a few times. Mod 5 also equals to 1, which means 6 and 31 are congruent mod 5. Yeah, which means they give you the same remainder when divided by 5. Of course, as you can very clearly see, 31 minus 6 equals to 25, which is a multiple of 5. Yes? Okay, so once we establish that, now what we can do is we can apply this principle to powers of 2. So what it means is, what we have here is we are looking for 2 numbers, basically, if they are multiples of, if difference of these 2 numbers are multiples of 8,479. It means they're congruent. They are congruent with respect to the modulus of 8,479. Yeah, that means they will give you the same remainder. That means 2a mod 8,479 will have to equal to 2 to the power of b mod 8,479. Yeah, so this first power of 2 divided by 8,479 should equal to the second number, 2 to the power of b, and divided by 8,479. Yeah. So how do we? That means it will have to complete at least one cycle with respect. Yeah. So because after each cycle, you get the same remainder. So in here, it's cycles of 3. 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah. So the cycles of 3 here, because the divisor is 3. Now, of course, what are the powers of 2? We can apply the same procedure because we can apply the same procedure. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on and on. Yeah. Of course, one thing is convenient is we're not actually incrementing. So here is incrementing 1 at a time. We're not incrementing 1 at a time. So we may not have to, the cycles may not be complete. The cycles may not complete the same way here. However, we don't actually know what it will be. So what we can do is we can guarantee that a cycle will have complete at least one cycle by go all the way up to 2 to the power of 8,479. Yeah, because here we don't know how many cycles continued, but because we know that here, all of here has 8,470 numbers here. Yeah, so we know that we have more than enough to complete at least one cycle with the modulus of 8,479. Yeah. So what we know is because we have completed at least one cycle, then that means at least 2 of these numbers will have the same remainder. At least somewhere here, somewhere inside here, there will be 2 numbers that will have produced the same remainder. Yeah. So because even if it increments 1 at a time, so if increments 1 at a time, by having 8,470 numbers here, we will have completed a cycle of 8,479, even if it increments 1 at a time. Of course, because these numbers, they're powers of 2, so they don't actually increment one at a time. So we probably complete more than one cycle between 8,470. Sorry, 1,880. Yeah. So 8,480 numbers. So that means it guarantees it ticks over. So it guarantees that 2 of numbers. So there exist, unfortunately. So there has to be 2 numbers, 2 to the power of A and 2 to the power of B, where they are the where they have the same remainder. With yeah, which means if they have the same remainder, that means the difference is a multiple of 8,479. Yeah, because in this case, because the divisor is 3, the modulus is 3, so it ticks over. It ticks over every 3 numbers. Here, the divisor, the modulus is 8,479. So even though it may be possible it may ticks over before 8,479 because these numbers don't increment one at a time. But by including 8,480 numbers here, it guarantees that it will have ticked over somewhere. Yeah, so we'll have the same remainder between 2 numbers somewhere along these 8,480 numbers. So that's guaranteed, which means they will have to be 2 numbers that have same remainder, and they will the difference, because they have the same remainder, means their difference is a multiple of 8,479. Yeah, where so times n, where n is a positive integer. Yeah, and so there is that.